Hello students, this presentation is about solutions. This is, of course, Mr. Brown. This is for the folks taking Science 110 at Sandhills Community College. And yeah, we're going to talk about stuff that has been dissolved in different stuff in this PowerPoint. I know that sounds really exciting to start off, but if you follow along with me, I think you'll see why we think some of this stuff is important. So on this slide, we will dive into why science classes and chemistry classes especially will often have a little section devoted to solutions. And the answer is solution chemistry is where a lot of the actual chemical reactions that kind of affect our natural world take place. I have a few pictures here to show you some examples of that, and you can see in the top picture, I think first and most obvious is all of the chemical reactions that drive what we think of and what we define as life happen in solution. What we mean is, so you are made up of cells, and we'll obviously go a little more in depth onto that when we do our biology sections closer at the end of the class, but I'm pretty sure most of us will be aware of the fact of this point. So you are made up of cells, so are your pets and other animals, and so are all plant life, so are bacteria and other microorganisms. They're all made up of these things we call cells. And inside these cells is basically a solution. So we have things dissolved in mainly water. You've probably heard that you are made up of 65% water, and that's usually what this is referring to. Inside your cells is water, and inside that water a bunch of other stuff is dissolved. And you have proteins and sugars and well, the organelles and stuff dissolved inside this solution, and comes from your food being broken down. These molecules are used by proteins to produce energy and produce structures to build new cells so that you can grow and regenerate. Furthermore, you can see in the next picture there, I've got a picture of a kind of a caverns that has been built, if you will, out of water dissolving limestone in the side of a mountain somewhere. So a natural source of water has dissolved away much of the material to form this beautiful cave that you see there over millions and millions and millions of years. And so it turns out, obviously, water is a big driving force behind the structure and function of our planet, with the oceans being an obvious influence. But as well, we have aquifers and underground water supplies that will dissolve minerals and drive the formation of new rocks and new caves and many, many other things. And then in the last picture there, you see we have a picture of a that would be your typical organic chemistry lab, where maybe some scientist trying to design a new drug to fight cancer or Alzheimer's disease or many of the other things that still plague us, but people are working on. And a lot of that work is done in solution when we're trying to design new molecules to help people or new materials. We often mix those things in water, or perhaps even some kind of organic solvents like alcohols and hydrocarbons and things. And so a lot of the practical chemistry that happens and a lot of the natural chemistry that happens around us is what we say in solution, where things that are reacting are dissolved in some substance. So that's why when we do these science classes, we like to stop and take a look and kind of characterize solutions and give you some of the background on how scientists classify and measure the solutions. Okay, so obviously, if we are going to talk about solutions, we need to define what is a solution, and we touched on it earlier in the different types of matter discussion about heterogeneous and homogeneous mixtures. So obviously a solution is a mixture usually involving a substance with another substance interspersed in it. And for it to be considered a solution, this special type of mixture, if you will, it must have a few characteristics. It must be homogeneous, meaning that the mixture is uniform, and we have some pictures here to guide us to the difference between heterogeneous and homogeneous. You can see on the top there we have a fruit salad of some sort, and we call that heterogeneous because we can see all the different little sections. I can see the individual strawberries and blueberries and grapes and pineapples and such. And then on the bottom there you have the homogeneous example, which is good old Kool-Aid. And we call that homogeneous. We consider that homogeneous because you cannot see the different parts. It's obviously a liquid, a water-based liquid of some sort, and there's some red food coloring in there. There's some flavoring in there, and there's some sweetener, sugar dissolved in all of that as well. And you can't really pick out the different parts. You can't say, well, this part's the sugar, and this part's the flavor, and this part's the red part, and this part's the water part. So we consider that a homogeneous solution. They're all distributed evenly together. And furthermore, for it to be a solution, we have to consider the particles that are dissolved. They should not, what we say, fall out of the solution. They will never settle out of the bottom. In a true solution, the things that are dissolved will never settle out of the bottom. Now, with the way some of us make Kool-Aid, some of the sugar may collect on the bottom over time, but it's still a solution. It just had a little too much dissolved in it, probably. But true solutions, most of that stuff, not all of that sugar, even if you have some really severely sweet Kool-Aid, not all of that sugar will fall out. It will stay that way for as long as you leave it covered so that the water doesn't evaporate away. You'll have that mixture of sugar and water in there. And so we've got a few more words that we're going to define here as well that you'll see here down at the bottom. It says solutes and solvents. When we talk about solutions, these are the two main parts of a solution. And the solvent is obviously the substance that dissolves the things. The most common universally being water. Water dissolves so many different things, and there's so much water here on Earth that has stuff dissolved. So to us, water is the most common solvent. And then the solutes are the things that are dissolved in that solvent. So as we go through the rest of these pages, you'll see those words referred to as we talk about these solutions. And here we go. You can see we got a few more comments about the solvents and the solutes. The solvent, again, is the substance that does the dissolving. It is the major component of the solution. It's usually easy to figure out which is the solvent and the solute, but in a few cases that we'll discuss in just a few slides, maybe that's not always so easy. And a good way to tell is the majority component of the solution is what you're going to call the solvent. In a solution, because the solution or because the solvent is the majority product, you can only have one of them. There can only be 1 liter of all the amounts of those substances in the solution, so there's only one solvent. And then, like I mentioned on the previous slide, water is known as the universal solvent because it dissolves so many compounds and because there's so much water around us with so much stuff dissolved in it, in our bodies, on the earth, in our pipes, in our lakes, in our rivers, in our streams, all of that. But just to kind of put this out there, not just water, obviously, can be all kinds of other substances. Some solvents can be liquids. We can think of stuff you may have been in contact with, like alcohols, acetone, terpenes, or things like paint thinners and mineral spirits, if you've ever worked with any of that stuff. But solvents don't just have to be liquids either. Gases can be solvents. The air that we breathe is a solution of gases, and sometimes even solids can be solvents, and we'll take a look at that over the next few slides. The solutes are the substances that can be dissolved. You can have more than one solute in a solution, like we've already discussed, or like I've already said. You can think of maybe like the ocean or lake water or rainwater. That's water with a lot of different things dissolved in it. Sugars, salts, minerals, all kinds of things. They are the minor parts of the solution, though. The solvent's the major, and then you have all the minor parts. And some common solutes, as you'll see in there. Solutes can be solid, like we can think of sodium chloride, which dissolves in water really well as being a good solute and a common solute. Sugar also is a common solute, dissolves in water really well. But they don't have to be. Carbon dioxide is a good solute that you can think of as something dissolved in water. That's how we make carbonated drinks, which I'm sure everybody has some exposure to. We dissolve the gaseous carbon dioxide in the liquid water, and that gives us what we call carbonated beverage. So here on this slide we have examples of the common solutions that people may have contact or experience with but may not realize are actually solutions. The first one that you see there was mentioned on the previous slide. Earth's atmosphere is about 78% nitrogen, so that would be our solvents. And the solutes you see are things like oxygen gas, which is the important part of the atmosphere, and that's the part we need. Our atmosphere generally sits at about 20% oxygen gas. And then we have, obviously, or of course, some carbon dioxide, the levels of which have become a major concern as of late, as of in the last 100 years probably. But it generally only occupies about 0.01%. But as that concentration becomes greater and greater and greater, it's definitely more of a concern. And we also have something called argon. Argon is just a really inert gas. It doesn't really help or hurt anything. But it sits at about 1% of our atmosphere. And then we have varying amounts of water vapor also distributed in that atmosphere. We have a lot of water vapor, for instance, here in North Carolina. But if you move out west to some of that desert area, they don't have so much water dissolved in their air. And then the next one we have isopropyl alcohol or rubbing alcohol. So if you go to the drugstore or the pharmacy and pick yourself up one of those solutions of rubbing alcohol, those solutions are generally composed of two liquids. They're composed of isopropyl alcohol and water. And the content of isopropyl alcohol can range anywhere, usually in those drugstore concentrations, 50 to 90%. And so I guess if it was a 50-50 mix, you could call whichever the solvent that you wanted to. Probably water, just because water is such a common solvent. But as you go over 50% alcohol, the alcohol becomes the solvent and the water becomes the solute. And up until you can buy 100% isopropyl alcohol at the drugstore. So that would no longer be a solution. That would just be the compound isopropyl alcohol in a bottle. But if it's anywhere between 50 to 90%, it's a solution with the solvent being alcohol and the solute being water. And then we also talked about this next one on the last slide as well, where we have a gas dissolved in a liquid. And I would say everybody probably has exposure to these, and that's carbonated drinks. But you also I have listed there some of the solutes. You also have sweetener. A lot of times sugar, but in your diet drinks you have things like aspartame or acesulfame, potassium acesulfate. And you have flavors, natural flavors, oils off different fruits and plants and things to give it different flavors. And that whole solution is what we call a soft drink. And then I have another example of a solid metal solution, steel, which is used in all types of applications. I have some kitchen knives down there, but it's obviously used in building materials and medical materials and jewelry and cutlery and just so many cars, so many applications for steel. And steel is made by dissolving things like carbon, graphite carbon, and then some other metals into elemental iron metal. So in the next few slides, we'll discuss some characteristics of solvents and solutes. And we'll start with the idea of solubility and whether something is soluble or insoluble in something. And of course, not everything will dissolve in a given solvent. Water can't dissolve everything. There's some rocks it can't dissolve. There are some, it can't dissolve oils and fats, for instance. Those two substances do not mix. They're incompatible and they don't dissolve in one another. And we'll talk about the ability of solvents to dissolve things to varying degrees. So what we're going to talk about is the concentration of a solution. And the concentration of a solution, you can see in the picture there, it describes how much of a solute is dissolved in a solvent. So in a solvent that has a lot of the solute dissolved in it. For instance, if you had just a small glass of water and you poured a lot of salt in it and you stirred it up till all that salt dissolved, that would be a concentrated solution. But on the other hand, we can talk about dilute solutions which only have a small amount of solute dissolved in solvent, and that would be like having that same cup of water and taking one salt crystal and dissolve it in that solution. It would still be a solution. You would have a little bit of salt dissolved in that solution, but it's very, very dilute. You could probably drink it, not even notice the effect. So the first stop on the solubility train is whether or not something is actually soluble versus the word insoluble. And soluble describes things that will dissolve in a solvent. For example, the most easy example is probably salt is obviously soluble in water. There's tons and tons. There may be more salt water than anything else on this planet. So not really, but it might seem that way if you look at the size of the oceans. Salt is obviously very soluble in water. And then the other good example for the word insoluble is the fact that oil is insoluble in water. So I'll take a second here to stop and discuss with you why some things like, say, salt are soluble in water versus why some things like oil are insoluble in water. And it comes down to this characteristic of individual molecules that scientists call polarity. And I won't get too far into it. We'll just say that some compounds or some molecules are polar and some molecules are nonpolar. Now what it has to do with is electrical charge. In polar compounds, the electrical charge is not very evenly distributed. It has places where there's a lot of negative charge and places where there's a lot of positive charge, and we call those poles, and those would be polar compounds, kind of like poles on a magnet, plus and minus. And then you have nonpolar compounds, and in nonpolar compounds, they have very symmetrical molecules, and all of their electrical charge is spread out really, really evenly. So there's none of these positive areas and negative areas. There's none of these pluses and minuses. There's no poles. They're nonpolar. And so what we've determined is things that are polar like to dissolve in things that are polar, and things that are nonpolar like to dissolve in solvents that are nonpolar. And so that's why oil and water don't mix. Oil is a nonpolar molecule, and water is a very polar molecule. So water likes to dissolve very polar things. Salts and ionic compounds are very polar, therefore they dissolve very well in water. Fats are not very polar, they're nonpolar. They don't dissolve very well in water. They do dissolve well in things like gasoline would be a good example. They dissolve oils and fats. Other hydrocarbons, very nonpolar, and so they dissolve those things very well. Something else that is noted when a solution is formed is that the properties of the solvent, in particular, the boiling point and the freezing point of a solvent, will change when things are dissolved in it. Most of the time, oftentimes, it doesn't matter what the identity of the solute is, especially in the next two examples, only how much is dissolved in it. So in the first example we have here is boiling point elevation. So when you dissolve anything in a solvent, and the best example, as I've said many times throughout the slides, is water. We have a picture of antifreeze being poured into a car. So antifreeze is a mixture of this stuff called ethylene glycol, and it's just added into water to go into your engine. And while it's called antifreeze, it does help to lower the freezing point of water so that it doesn't freeze and bust up your engine when the water expands. It also raises the boiling point of that water. Anytime you dissolve something in water, it raises the boiling point of the water, of the solvent. And what that does is it helps the water from turning into vapor inside your engine, which helps it cool off better while you're driving it and as it gets hot. So not only does antifreeze keep your water from freezing in your engine, antifreeze, hence the name, it also is kind of like anti-boil as well, because it raises the temperature with at which the water would boil. When you put salt, if you're cooking pasta on the stove and you put salt in your water while you're trying to heat it up, you actually raise the boiling point of that water. Now, unless you put a ton of salt in there, which would probably taste pretty bad, you're not making a big difference. But when you shake a little bit of salt in your water that you're boiling, you're actually making it just a little bit tougher to boil that water. It might go up by 0.1 of a degree or something, but it's just a little bit harder. It will take just a little bit longer to boil that water if you put salt in it. And then you have freezing point depression, meaning that the freezing point of those solvents gets lower. It goes down further. And this is the idea. You can see the truck spraying salt on the roads there. What the reason is the salt dissolves in the icy water that is there, and instead of freezing at 32 degrees Fahrenheit, the water might go all the way down to 25 degrees Fahrenheit before it turns into ice, which if it's sprayed at somewhere that's maybe 30 degrees, that will help out. We'll turn the ice on the road back into liquid water and allow the cars to get some traction. In some places the salt will not work because as you get down to 0 and -5 degrees and stuff, it's just not strong enough. It doesn't depress the freezing point low enough, and you'll still just get ice. So over the next few slides, we're going to characterize the concentration of solutions a little bit. And we're going to start with just the qualitative characterizations of unsaturated, saturated, and supersaturated. So it might be best to have an example to describe these. Let's imagine we are dissolving some sugar in a glass of water. We are trying to make some tea or something. And we put a tablespoon scoop of sugar in our tea, and we stir it and we dissolve it. At that point, you can probably imagine that another tablespoon scoop of sugar would dissolve in the water. And at that point, we would call the solution unsaturated, meaning that it can still hold more of the solute. The solvent water can hold more of the solute sugar. At some point, however, it does reach a maximum amount. So you keep putting a few tablespoons in there. You really like sweet tea, and so you reach the point where the solvent water can no longer hold any more sugar. What happens is, as you put more in there, some of it will stay solid. No matter how much you stir and stir and stir and stir and stir and stir, you still would be left with some solid that would settle to the bottom if you left it sitting. We call that point saturated. The solvent can no longer hold any more solute. And then, of course, you can see that you can get super saturated, meaning in some ways, under certain conditions, you can get more than usual to dissolve into a solvent. And so if you had that tea and you really wanted some really sweet, you could probably warm that water up and more of that sugar would dissolve. Now, you wouldn't consider it super saturated until what happens is you can cool that solution back down and it will hold that solvent a little more than normal. But generally over time, some of it will still start to kind of fall out of the solution and collect at the bottom. So down here in the South, a lot of us like to make super saturated sweet tea, where you heat the water up and you dissolve the sugar, and then you dissolve your tea mixture in there, and then as you leave it in the refrigerator, you had so much sugar in there that water collects at the bottom of your tea pitcher. But that might be a good example of a super saturated solution. So on the next few slides, we'll look at some graphs that tell us whether a solution would be saturated, supersaturated, or unsaturated. What would science class be without reading a graph or two, right? You can see the name of this graph is a solubility graph. It's going to tell us whether a solution of potassium iodide is saturated, potassium nitrate is saturated, and as well as sodium chloride. On the y-axis, you can see the solubility, which says grams per 100 centimeters cubed of water, or grams per 100 milliliters of water. And you can see that the x-axis says temperature. The way this graph can be read is somebody took some beakers, and in these beakers, the scientists put 100 milliliters of water in each. And they heated the beakers to different temperatures. Maybe this one was 10, and this one was 20, and this one was 40, and this one was 50, and this one was 60, and so on and so forth. And into each of these beakers, they would drop some of the compound that they were studying. So for sodium chloride, at the 10-degree beaker, they would put some sodium chloride in and dissolve it. And they would put some more in and dissolve it. And they would put some more in and dissolve it. And they would do this until they got to the amount of sodium chloride, the number of grams of sodium chloride, that 100 milliliters of water would no longer dissolve anymore. At what gram, at what weight of salt would no more dissolve? Would some still stay solid when you kept putting it in this 100 milliliters of water? And so we can see that the data, they plotted their data for each of those temperatures, probably, or it looks like maybe every 15 degrees, all the way between 0 and 100, and drew a line that shows at different temperatures how much sodium chloride will dissolve in 100 milliliters of water. They did this for potassium nitrate and potassium iodide as well. Potassium iodide has some medical applications, so it may be useful there. And potassium nitrate is a well-known fertilizer, so this information might be useful for a farmer mixing up solutions of fertilizer to apply to their fields. And so we'll see here on the next few slides some questions about reading a solubility graph. And they work like this. I'll give you a few of these examples and work through some with you. The first one we see says how much KNO3, which is potassium nitrate, will dissolve in 100 milliliters of water if the water has a temperature of 60 degrees Celsius. So we want to read our graph by pulling out that information from the clues in the question. We can see that we're looking at 60 degrees Celsius, and we notice we're talking about 100 milliliters of water. Sometimes in these questions you can see that 100 milliliters change, and you may have to do some extra math, but since all of our graphs are read in 100 milliliters, I'm just going to leave it the same. So how much KNO3 will dissolve in 100 milliliters of water? So you will go to the 60 degree mark, and you will go and find the potassium nitrate line at 60 degrees. Which is this line here. At 60 degrees, we cross the potassium nitrate line, which is this line here, at this point right here. And that would correspond to our y-axis, somewhere between 100 and 130. I'm just going to guess, since it's closer to 100, I'm going to guess 110 grams. So if you had 100 milliliters of water and that water had a temperature of 60 degrees Celsius, you could dissolve about 110 grams of potassium nitrate in it before whatever extra you put in there would not dissolve any longer. The next question says, if I have a saturated solution of sodium chloride in water at 75 degrees Celsius that is saturated, how much salt will be dissolved in 100 milliliters of that solution? So this is very much the same question. If I have a solution of sodium chloride in water at 75 degrees Celsius, so 75 degrees Celsius is this line here, that is saturated, how much salt will be dissolved in 100 milliliters of that solution? So sodium chloride at 75 degrees Celsius looks like it's saturated almost right on this line right here. That looks to be the 40 gram line. So that would be 40 grams in our 100 milliliters of saturated sodium chloride solution if that solution was 75 degrees Celsius. Then our last question says, true or false? Solution temperature affects the solubility of potassium nitrate much more than sodium chloride. So what this question is asking is, which compound has a bigger difference in how much can be dissolved based on temperature? So let's look at our graph here. Let's consider potassium nitrate. We can see that this line right here is a very steep curve. Very steep curves generally indicate very much change on a graph. You can see at 0 degrees Celsius, 100 milliliters of water will only dissolve about 10 grams of potassium nitrate. But at 90 degrees Celsius, 100 milliliters of water will dissolve almost 200 grams of potassium nitrate. There's a huge difference. Sodium chloride, on the other hand, has this very, very flat line. A lot of times when you see flat lines on graphs, that is indication of not very much change. And in fact, at 0 degrees Celsius, so almost frozen water will dissolve almost 40 grams of sodium chloride. But almost boiling water will still only dissolve about 40 grams of sodium chloride. Sodium chloride is not very affected by temperature. So, solution temperature affects the solubility of potassium nitrate much more than sodium chloride. That looks absolutely true to me. One final example to close this out. If a sodium chloride solution at room temperature has 10 grams of salt dissolved in 100 milliliters of water, is the solution saturated, supersaturated, or unsaturated? So again, sodium chloride, the line can be found here. When my pen works. Sodium chloride's line is here. So at 20 degrees Celsius, which would be somewhere between 15 and 30, a little bit closer to 15, has 10 grams of salt. So somewhere in this area only has 10 grams of salt. It looks like that solution probably would hold more sodium chloride. So we would say that that solution is unsaturated, because we could dissolve more sodium chloride in our 100 milliliters of water.